Only a small part is remain from the previous section, and that's the coordinate coupling and principal coordinates. For this purpose, we can consider a system with 2 degrees of freedoms, which is consists of an elastic beam, which is located on two elastic supports with a stiffness K1 and K2, and with mass M and mass moment of inertia J naught. The position of the mass center for this system is located at point CG, as here you can see at this point, which it has a distance of L1 with point A and a distance of L sub 2 with point B. We want to extract the equation of motion for this system, but as I told you, the first step is to choose a coordinate system. We should consider the coordinate system and the degree of freedom to extract the equation of motion. In this system, we can consider different sets of coordinates, and in fact, the motion for this system can be described with different degree of freedoms. For example, the first one, we can extract the equation of motion for the coordinates x1 and x2, which they are the displacement or deflection of point A and B respectively. Or we can use the coordinates x and theta, which x is the displacement or deflection of the mass center, and theta is the rotation of the bar about the mass center. And this is another set of the coordinate system. Or we can use x1 and theta. For example, here you can see x1, which is again the displacement of point A, and theta is the rotation about the mass center in clockwise direction. Or you can use x2 and theta, and it's up to you. So different coordinates can be used, or we can use another set that we can use is the y and theta, which y is the deflection for an arbitrary point P, and theta is the rotation about the mass center again, of course, sorry, about the point P in clockwise direction. Here this is theta. This theta is different from the previous theta. So this is another coordinate system that we can use, and we can extract the equation of motion based on these two parameters. So the first step to extract the equation of motion for a system with 2 degree of freedoms similar to the STOF system is to choose the degree of freedom, which parameter or which coordinates will be used, will be employed to extract the equations of motion. Here in this session, we want to discuss the effect of these coordinates on our equation of motion, and consequently the effect of these coordinates on the result and response. So for this purpose, we can extract the equation of motion with different coordinates, which all of these coordinates are called generalized coordinates. And today we want to extract the equation of motion for different coordinates. The first assumption, we want to extract the equation of motion for this system by employing xt and theta t as our generalized coordinates. You know that because this is a system with 2 degree of freedoms, only 2 coordinates can be sufficient for the equation of motion for this system. So here we are using xt and theta. And for this purpose, if you write the Newton's second law for this system, and by writing the, for example, the moment equation about the mass center and also the force equation in vertical direction, you can extract two equations, and if you write it in the matrix form, you can see we have a system of two ordinary differential equations in this form. As you can see in the first equation, we only have x double dot because the coefficient of theta double dot is 0, but we have x due to this term and also theta in the first equation. But in the second equation, the coefficient of x double dot is 0, but the coefficient of theta double dot, it's not 0 and it's equal to j naught, or the mass moment of inertia about the mass center. The coefficient of x is k2L2 minus k1L1. As you can see, due to this term, we have the term x in the second equation, and also the coefficient of theta, which is this term, and due to this term, we will have theta in the second equation. So you can see we have a coupling because in the first equation, both x and theta are paired in the equation, and also in the second equation we have x and theta. But we can simplify this equation if we assume that k1 times by L1 was equal to k2 times by L2. Under this condition, you can see the non-diagonal components in the matrix of stiffness. I mean this component and this component were equal to 0, and under this condition k1 L1 was equal to k2 L2, then the first and second equation will be independent, and you can independently solve this equation and obtain the response by solving two independent ordinary differential equations. So this is the condition that we can use to separate these two equations. But in the general condition, you can see that these two equations are coupled, and the response of x is dependent on the response of theta. In fact, in this system, we will have both rotation and translation during the vibration. But if this condition was, I mean, K1 was equal, K1 L1 was equal to K2 L2, then we had the pure rotational or pure translational motion. Okay, so this is the condition. And also here we can conclude that when the non-diagonal component of the stiffness matrix is not equal to 0, or in the general condition for this example, we call it that there is a coupling, elastic or static coupling for this system, because the stiffness matrix is not diagonal and non-diagonal components are not equal to 0. So in this type of systems, we call that the system is static or elastic coupled. Okay, but the second coordinate system that we can consider in this system is y and theta. If you extract the equation of motion for y and theta, you can see in the first equation the coefficient of y double dot is m, and in the coefficient of theta double dot is m times by e, which e is the distance between arbitrary point P and the mass center of the bar or of the system, in fact. In the second equation, the coefficient of y double dot is again m times by e, and the coefficient of theta double dot is jp, which jp is the mass moment of inertia about the point P, about the arbitrary point P. Also, in the first and second equation, we have both terms y and theta. Due to these terms, as you can see, the stiffness matrix is not diagonal, so both terms or both coordinates are appeared in the first and second equation. In this case, we call it that because we have a non-diagonal matrix of coefficient for the acceleration, we call it there is a dynamic coupling or mass coupling, as well as the static or elastic coupling. Okay, so you can see by changing the coordinate system, the equation of motion will be changed. I mean here by changing the coordinates from x and theta to the y and theta, the equations will be dynamically coupled. But by moving the coordinates from y and theta to x and theta, you can decrease the coupling level of your equations, and you can vanish the dynamical coupling in your equations. So definitely there will be another coordinate system that we can, by changing to that coordinates, we can vanish the elastic or static coupling in our equations, and we can find a coordinate system that under that condition you will see that we will have two uncoupled or two independent ordinary differential equations, and you can separately solve these equations and obtain the response. Okay, so we can conclude some conclusions from these points. The first one, if the stiffness matrix or matrix K, which is the coefficient of the displacement x and theta, or x1 and x2, if this matrix is not diagonal, the system has elastic or static coupling. If the damping matrix or matrix C, which is the matrix coefficient of the velocity, if this matrix was not diagonal, the system has damping or velocity coupling. And if the matrix M, sorry, this term, it must be M instead of C. In fact, it must be M, the mass matrix. If the mass matrix was not diagonal, the system has mass or inertia coupling, and both velocity and mass coupling come under the heading of dynamic coupling. I mean, when we have mass or damping coupling, generally we call it dynamic coupling, and when we have stiffness, non-diagonal stiffness matrix, it will be called elastic or static coupling. The system vibrates in its own natural way regardless of the coordinates used. So when you solve the equation of motion, assume that in the previous example we extract the equation of motion using two different coordinate system, and we want to solve this. Definitely the natural frequency is a characteristic which is related to the nature of your system. I mean, by changing the coordinate system, the response will be remain the same, the characteristic of the system will be remain the same. I mean, is the natural frequency is the same, and when you solve these equations, you will extract the same natural frequency or the same eigenvalue for your system. But definitely by changing the coordinates, you can change the difficulty level of your equations. And in terms of the mathematics, when you want to solve a system of two coupled ordinary differential equations, it's an important point to decrease the difficulty level or decrease the coupling level of the equations. So we can definitely choose specific coordinates to decrease the level of the difficulty in our system. The next one is, it is clear that the nature of the coupling depends on the coordinates used and it's not an inherent property of the system, as I explained. And also it is possible to find a coordinate coordinate system which gives equation of motion that are uncoupled both statically and dynamically. So this coordinate system, which is called principal or natural coordinates, and in later we will discuss that how we can extract and how we can find this coordinate system, is an important parameter in our 2 degree of freedom systems that we can find. And under this condition you will see that the equations of motion will be separated, and you can separately solve each equation and obtain the response for that degree of freedom. I mean, for example, in the previous example for x and theta, under that condition when k1 L1 was equal to k2 L2, you will see that the equations will be independent, and you can solve the first equation for x and obtain the x for from the first equation, and you can solve the second equation and obtain theta by solving the second equation. And you will see that we will have two independent or two uncoupled equations. So this is one important uh, point in this section, and later we will discuss that how we can obtain the principal or natural coordinates. So the main advantage of using principal coordinates is that the resulting uncoupled equations of motion can be solved independently of one another. So when you use the natural coordinates, in fact, instead of 1 2 degree of freedom system, you will have two system of single degree of freedom, and you can use the previous methods to solve these equations. Here in 2 degree of freedom system, you will see that when you deal with the force vibration, sometimes it's very complicated to obtain the analytical response for a system with 2 degree of freedom when the coordinates are coupled. But by using the natural coordinates, we can convert it into two independent equations. And by using the previous methods such as convolution integral or Laplace transform, we can easily find an analytical solution for the equations of motion, and we can obtain the response of a system with 2 degree of freedoms subjected to different external force. So this is the coordinate coupling and principal coordinates, and as I told you, later we will discuss the different methods to extract these coordinates. Maybe continue with one example. Here we have a rigid rod of negligible mass and length 2L, which is pivoted at the middle point and is constrained to move in the vertical plane by springs and masses as shown in figure. Find the natural frequencies and mode shapes of the system. Here, this example, we will use the theta and x as a degree of freedoms, or as the generalized coordinates in our example. Theta is the rotational degree of freedom of this rod in counterclockwise direction, and x is the vertical motion or vertical displacement of this mass m. And by using these two coordinates, we can easily extract the equation of motion. And by using the Newton's second law and the free body diagram of this system, we can extract the equation of motion for this system. If we assume that the system is moving in the positive direction of x and theta, we will have some initial deflection in the springs due to these masses. So as you can see, we neglect the weights of the masses in the free body diagram, and only we consider the force due to the springs during the motion. So we will have one force due to this spring, one edge of this spring is fixed here, as you can see, and the other edge here is moving, and the displacement of this edge is equal to the displacement of mass 2m, and it's equal to k, it's equal to L times by theta. This length is L, and because the theta is small, so this displacement is equal to L times by theta. So this is the deflection or displacement of this point. So the force in this spring is equal to K times by L theta, or K times by the displacement. We have another spring here in the right side of this rod. Both edge of the spring will move. So the force in this spring is equal to the displacement of the both edge. When the rod is rotating in counterclockwise direction, this mass 2m will go up, so this edge of the spring will go up, and when xt, the mass m will move in positive direction of xt, it will go down. So from two sides, the spring k will be pulled, and so definitely we will have a reaction for both sides, and it's equal to k times by the displacement of both sides. Here, because from the both side, the spring is subjected to the extension, so the displacement is equal to the summation of both edge displacement. For this edge, the upper edge, the displacement is equal to L times by theta, similar to the previous spring. But the lower edge, the displacement is equal to xt, because it's fixed to mass m, and the displacement of mass m is xt. So finally, the force in this spring is equal to k times by L theta plus x. And consider if xt was in upward direction. I mean, for example, if we assume that xt was in upward direction and it was the xt, then the force in this spring was, of course, by using this direction, was equal to k times by L theta minus x. But here, because we assume that xt is in downward direction, and this edge of the spring will be under extension and it will be pulled, so the here for calculations, the force in the spring, it's equal to k times by L theta plus x. Okay, so the direction of this force is important, but according to this assumption and this direction for the displacement, here we will have k L theta plus x. And finally, we have one spring here, which the force in this spring is equal to the spring stiffness k times by the displacement, which we have one fixed edge here, you can see, and the other edge which is fixed to mass m. The displacement of this edge is equal to xt, and finally the force in this spring is equal to k times by x. So this is the free body diagram, and now we can write the moment equation and force equation for mass m and rigid bar, and we can extract two equations of motion for this system. So as you can see, the first one is the moment equation about this point, if we call it O. If you write the moment equation about point O, as I told you, we will have one moment due to this force k L theta multiplied by its arm, which is L. We have another force k multiplied by L theta plus x, again multiplied by its arm, which is L. And finally, it must be equal to the mass moment of inertia about point O. In this system, the mass of this rod is negligible according to the problem description, but we have two particles with mass 2m, as you can see here. So this system, it has a mass moment of inertia of 2m times by L squared. You know that the mass moment of inertia of a particle with mass m, assume that this is particle with mass m, when you are calculating the mass moment of inertia about this point O for this particle, and this distance is equal to d from dynamic, you know that the mass moment of inertia of this particle about point O is equal to md squared. In this case, the mass is equal to 2m and d is equal to L. So it's equal to 2 times by m times by L squared multiplied by theta double dot. And also we have another mass with mass 2m in the right direction. So it's equal to 2m times by L squared times by theta double dot. And for mass m, if you write the force equation in y direction or in vertical direction, we will have two forces, kx and also k times by L theta plus x. And finally, it must be equal to the mass times by x double dot. And if you simplify, you can extract the second equation. So we have two equations of motion, and we can write it in matrix form. And as you know, in the first equation, we have theta double dot, we have theta and x, but in the second equation, we have x double dot, x and theta. So this equation, according to the previous discussion in previous slides, this equation of motion will have the static or elastic coupling, and there is no dynamic coupling in this system. Okay, so according to this coordinate system, of course, x and theta. So if you write the equation of motion in matrix form, it will be in this form: matrix m multiplied by acceleration plus matrix k multiplied by displacement. It must be equal to 0. And now to find the natural frequency, we need to form the frequency equation or characteristic equation. The characteristic equation will be obtained from the determinant of this matrix k minus m omega squared. And if you calculate this matrix and find the determinant of this matrix k minus m omega squared, you can extract this characteristic equation or frequency equation. To solve this equation, you know that we need to substitute omega squared is equal to alpha. Then we will have an equation, an algebraic equation from order 2, and you can solve this equation and obtain two roots, alpha 1 and alpha 2. Omega 1 is equal to a square root of alpha 1 and omega 2 is equal to a square root of alpha 2. So these are the natural frequencies or the eigenvalues of this system. As you can see, omega 1 is equal to 0 0.59 times by square root of k divided by m, and omega 2, which is more than omega 1, is 1.46 multiplied by square root of k divided by m. So this is a system with 2 degrees of freedoms, and we must extract 2 natural frequencies for this system and 2 mode shapes. For the next step, we need to substitute omega is equal to omega 1 in this equation and calculate the relation between x and theta and obtain the first and mode shape. And for the second mode shape, we need to substitute omega is equal to omega 2 in this equation, if we call it equation 1, and then we can calculate the second relation and the second mode shape. If you substitute, you can extract this relation. Omega is equal to omega 1, so we can conclude that the amplitude of x is equal to minus 0.6 times by L times by theta, or amplitude of theta. So this is the first mode shape, and for the second mode shape, we need to substitute omega is equal to omega 2 into the equation 1 in previous slide. And then we can conclude that the amplitude of the x is equal to 6.6 times by L times by amplitude of theta. And this is the second mode shape. Okay, so these are the natural frequencies and mode shapes for this system. Any question from this example? Okay. Okay, finally we finish the concepts for last week. Okay, for this week we will discuss the force vibration analysis, semi-definite systems, and solution using the Laplace transform. For the force vibration of a system with 2 degrees of freedom, the general form of the equations of motion will be in this form. As you can see, we will have the matrix M. This is the general form, and as you can see, we have both elastic, static and dynamic coupling in the system. We have non-homogeneous term F1 and F2. Here we have matrix M, which is the matrix of mass. We have the damping matrix, and also we have the stiffness matrix. To solve these equations, we need to consider the external force. To solve these equations in this course and in this section, we assume that the external force has a general form, a general exponential form, as you can see here, with amplitude f j naught, which j is equal to 1 and 2. It means that f1, the first component, the first non-homogeneous component in the first equation, is equal to f sub 1 0 multiplied by exponential I omega t. As you know, this exponential I omega t in fact is a harmonic function of time. So we want to find the response of the system subjected to a harmonic external force or subjected to a harmonic excitation. And also for the second non-homogeneous term, F2, which is equal to F sub 2 0 exponential I omega t, which omega is the frequency of the excitation. So we want to find the response of this system subjected to a harmonic excitation, and for this purpose we can consider the response similar to the single degree of freedom system. We can consider the response with the same harmonic and with the same frequency. Xjt, which is x1 and x2, is equal to uppercase xj multiplied by exponential I omega t. So you can see, similar to the single degree of freedom system, we assume that the response is a harmonic function with the same frequency omega, but we need to obtain the amplitude of the response. So to find the amplitude of the response, we need to substitute this xt or this response in the main equation similar to the S2F system to obtain the amplitude, and we can solve for the amplitude of the equation. For this purpose here, in S2F system, we only have one equation, but here we have a system of equations. So instead of one coefficient, we have a matrix of coefficient. And instead of the response, we have a vector of the responses. So we can consider another method to solve this equation, and we define a new parameter which is Z, and it's the mechanical impedance of our system. If we define the mechanical impedance according to the matrix M, C, and K, it will have four components, which, as you can see, R and S are equal to 1 and 2. It means that it will have this is a matrix with four components. We will have a matrix something like this. The first column and first row, it will be Z1 1. The first row and second column, it is Z1 2. the second row and first column is Z2 1, and finally the second column and second row, which is Z2 2. So here you can substitute, for example, for Z1 1, here R is 1 and S is 1. Again, R is 1 and S is 1. So it will be minus omega squared multiplied by M sub 1 1 plus I omega. Here R is 1 and S is 1. So it is CR C1 1. C1 1, if we assume that this is the matrix of C, C1 1 is this component. Okay. And K11 or M11 is again the same component similar to C11. There, for example, K11 is the first component in the first row and first column in matrix K, or for M we have the same. So we can obtain a matrix which is called mechanical impedance, as I told you. And now we can find X by using the matrix calculations. Here, the matrix impedance, mechanical impedance multiplied by the amplitude vectors, which is x1 and x2. This is the amplitude vectors. It's equal to f naught, which f naught vector, in fact, is the amplitude of the excitation. F sub 1 0 and F sub 2 0. So easily from the matrix calculations and matrix algebra, vector algebra, we can obtain that X is equal to Z inverse multiplied by vector F naught. So we can find X easily by using the inverse of matrix Z. And you know that the inverse of matrix Z is equal to this term. You can calculate the inverse of this matrix, and finally by multiplying by f naught you can obtain the x1 and x2, which x1 and x2, these two terms are called the amplitude of the response for the first and second coordinates. So you can see we obtain the particular response of a system with 2 degrees of freedom subjected to a harmonic excitation. So it's very important here. In this section, we only obtain the response of a 2 degree of freedom system subjected to a harmonic excitation. But similar to the single degree of freedom system, you know that we will have different type of excitation. I mean, for example, we can have periodic excitation or we can have non-periodic excitation. And for the single degree of freedoms, we use different methods such as Laplace transform or convolution integral. And here you will see we can use the Laplace transform as well for the system with 2 degree of freedoms. But this procedure is only applicable for the systems with harmonic excitation. Okay, we continue with one example. We want to derive the equations of motion of the system shown. Here we can see that we have a system with two masses m1 and m2. The coordinate system is considered x1 and x2, but this system is subjected to a base motion. As you can see, the base motion or the equation of the base motion is called yt, and it will affect as a harmonic excitation. So to extract the equation of motion, we can write the Newton's second law separately for mass m1 and m2, and for each mass we can write the Newton's second law in vertical direction. For the mass m2, we will have a spring k2 and damper c2, but for mass m1, we have k1 c1 in addition to the spring k2 and damper c2. But the point is here that in this for mass m1, in this spring k1 and damper c1, both ends of the spring and damper are subjected to the motion. One edge is moving by x1 and the other edge is moving by yt. So we can write first we can plot the free body diagram for this system, and then we can write the equation of motion for this system. If we plot the free body diagram, we will have the force due to the springs and dampers, and we neglect the force of the weight, or we neglect the weight in the equation of motion, because the weights will create some initial deflection, and we neglect the initial deflection in the springs, so we can neglect the weight as well. So for the mass m1, the summation of the force must be equal to m1 x1 double dot. The summation of the force for this mass is 1 due to the spring K2, 1 due to the spring K1, 1 due to the damper C2, and 1 due to the damper C1. And as I told you, all of the springs have the movable edge. K2 subjected to the motion of x1 in one edge, and the other edge is moving by x2, so the force in K2 is equal to K2 x1 minus x2 or x2 minus x1. It depends on the direction of the force. And for the C2, it will be C2 multiplied by x1 dot minus x2 dot, or x1 x2 dot minus x1 dot. Again, according to the direction of these vectors, you can consider a different sign for x1 dot and x2 dot. Also the same procedure for the spring K1 and damper C1. The force in spring K1 is equal to K1 times by x1 minus yt, or yt minus x1, and the force in the damper C1 is C1 multiplied by x1 dot minus y dot, or y dot minus x1 dot. As in previous example I mentioned, because here you can see, for example, for a spring K1, the lower edge is under pressure, or it is compressed, but the upper edge is under extension, or it will be pulled. So the sign for x1 and y will be different. I mean, it will be x1 minus y, or x minus x1 plus y, according to the direction. Here I assume that the direction is in downward direction, so the sign of x1 according to this direction must be positive. I mean, I will use the first term to calculate the force in this spring. But if you assume that x1 was in downward direction, I mean, assume that x1 was in this direction, then if you wanted to calculate the force in the spring K1, it was equal to K1 multiplied by x1 plus y, because both edge, according to this displacement, was under pressure, and it was compressed from the both sides. So the force was equal to K1 multiplied by the summation of x1 and y. But here we assume that the direction is in upward direction for x1 and x2. So you can see here the force in the spring K1 is x1 minus y, of course, because we assume that this force is in downward direction. So for each mass, we write the Newton's second law for the first mass m1 and for the second mass m2 by writing this equation and simplifying. And the equations we can write in the matrix form. As you can see, this is the matrix form. Here in the first equation, the coefficient of x2 double dot is 0, but we have x1 dot and x2 dot. And also we have x1 and x2 because both matrix C and K are non-diagonal. And also we have non-homogeneous terms in the first equation, but in the second equation this is homogeneous. But generally, because we have non-homogeneous term, this system is a system with non-homogeneous vector. So to solve this equation, we can use the previous method as I explained. By using the mechanical impedance matrix, you can find the response x1 and x2. Of course, because y is harmonic. If it was not harmonic, we cannot use this method. Okay, for today I think it's enough. We can wrap up this session if you don't have any question. Okay, any question from this part? No question? Okay, thank you for your attention, and we can continue tomorrow. Thank you. Bye.